Today I'm going to talk about machine learning for data-driven last mile delivery optimization. But first of all, I would like to thank for the invitation to be here, to attend this workshop, to present here. I got really inspired by the large number of excellent talks over the past couple of days. I'm really glad to be here. So this presentation is going to describe our approach for the last mile Amazon last mile routing challenge. And this is something I worked together with my former colleagues at Eindhoven, Sami and Paulo. So Sami is currently in Amazon as well, in Amazon Europe, Luxembourg, and Paulo, I guess he's in Ireland now in Etsy, working with data science. Before I begin, I would like to recap a little bit about the challenge, because this workshop is about consolidating contributions from different challenges. So I just want to swap in the memory again for the Amazon challenge, and then we can focus on the specific submission and the content of the talk. So we have some resources for the challenge. We have the official website. We have some publications. So the science team at Amazon published a paper describing everything you need to know about the data set. So if you like to use this data set for further research, well, everything you need to know is in this paper published in Transportation Science. There's the technical proceedings, in which the contributions of most of the teams are described there. And our particular submission is available as a preprint. That's the place where you can find it. And hopefully to be published soon in some journal. All right, so the motivation for the challenge, I guess the main motivation comes from the realization that drivers, they detain a lot of knowledge about the regions that they normally operate, that they normally serve. So a driver, after a few weeks, will develop a level, like an understanding of that particular region that goes much beyond what we can incorporate into route planners. And the idea of the challenge is that we can somehow try to learn this knowledge from the drivers and incorporate this knowledge when we create new plans for other routes. And there is also another thing that is important in the context of the challenge, is that we are dealing with real-world last mile routing. And we have a lot of things that we have to take into account at the same time. And it's kind of different from what we normally do in research, more stylized problems where we have a clear objective or set of objectives to optimize. And then we can develop our methodology towards that. In real world, there are a lot of things that we have to take into consideration, such as customer availability, congestion patterns, parking availability, and so on. And one thing that I would like to highlight is that the best balance among all those things that we need to consider may depend on the particular instance. So for example, if you are designing last mile delivery routes in Manhattan, it's going to be completely different than designing last mile routes for a countryside region. The set of things that you need to consider, they are very different. And decision maker or a route planner algorithm cannot possibly know every detail about every region the algorithm has to design routes for. But drivers, they can, because they are operating in that region every day. So in the challenge, we have some data made available by Amazon. So we have data at the level of routes, at the level of stops, and the level of packages. So one route contains multiple stops, and each stop has one or more packages. And we have, in the training set, we could observe the particular sequence that was used to serve those stops, and a route score, a qualitative measure, either high, medium, or low, describing the quality of this sequence. One particular piece of information that is very useful, and I think it was clear when we were watching the talks yesterday of the winning teams, is the zone ID, because it encodes some hierarchical structure where we have this concept of bigger zones, smaller zones, and tiny zones, or like macro zones, micro zones, and nano zones, as we call in our submission. And this is something that's going to become important in some part of the method. So some statistics about the data. I'm not going to, I mean, you can refer to that in the paper, but I just want to call attention to this last row here, % of packages with time windows, which is quite, it's generally low, and that somehow guided our decisions when we started thinking about how to solve the challenge, that we might just like drop these altogether because this creates additional complications, and then there's a not that high number of routes with packages with time windows. Okay, so the goal of the challenge is to develop some model. It could be a machine learning model, it could be operations research algorithm or a heuristic, whatever you want. But this model would have to could use the historical data, or probably should use the historical data, and then try to learn something from the data, and then after that, after this training phase, the model would consume new routes, new groups, new sets of stops, and will have to come up with good sequences for this particular group of stops. In terms of scoring, there is the similarity metric between the sequences that we had to provide in the challenge and the good sequences that we had to try to reconstruct as much as possible. And this is a Levenshtein-based distance metric. So basically, given two sequences, we'll return a number measuring how much those sequences deviate from each other. OK, cool. So we call this problem the route sequencing problem. And so just to align the terminology here, a route just represents a group of unsequenced stops. So a route is just a group of stops. There's no sequence associated with it. And the sequence is a permutation of the stops of the route, and then that corresponds to a solution to the RSP. So a route is an instance of the RSP, and the sequence is a solution to the RSP. And the goal is, given a route to a group of stops, find the best visiting sequence. So we can think about this problem in different ways, but if you try to model this problem somehow, you could think about having a set of instances and optimal solutions to an optimization problem. And now, based on this historical data, so we have any pairs of those instances and corresponding optimal solutions, you are now given a new instance, and you have to minimize from a given feasible region a certain cost function. So it's pretty general formulation here, so it doesn't really induce any obvious algorithm to solve that. But I like to think of this problem as having three different flavors. The first flavor is a kind of supervised learning flavor, because you want to learn from the historical data, and now you are given a new instance, and you have to predict or to come up with a good solution for that. It has a data-driven nature because it's basically driven by data. You don't have information about any distribution here. And finally, it also has an inverse optimization flavor because you don't know much about the function g. And again, highlighting that g may depend on the particular instance. So you have the dependence on the instance there. So the only thing that you know for sure is the feasible region, because you are, for the route sequencing problem, you know that it has to be a Hamiltonian tour covering all the stops. But that's really all you know, and somehow you need to come up with a solution for that. The framework that we are going to propose is general. We like to think that is general, and then can be used to solve problems stated in this form, as long as you implement three simple ingredients. We're going to talk about them. And then, in particular for the RSP, it gives good results, as we'll see. And those ingredients are sort of simple to implement. OK, so now describing the method that we proposed, we call it just pull and select. So it follows kind of common approach in the design of heuristics. It's basically generating a bunch of solutions, and then in the second phase, try to select what is the best solution from those that we generated in the first stage. So that's what we do. And if you want to get this method going, there are two things that we need. First is a solution generator, or how we call it, a sequence pooler. And second is a score model to evaluate how good a solution is for any instance. So this score model is pretty ambitious in its purpose, because it promises to measure the quality of any solution to any instance. And of course, that's more like the hardest part is here. Like the sequence pooler can be rather simple, but we're going to spend more time talking about how to train this score model. But starting with the sequence pooler, since we have this feasible region that consists of those Hamiltonian tours covering all the stops, we propose the sequence pooler based on the random insertion heuristic, which has a lot of nice properties and nice advantages, because every time that you run it, it's potentially going to generate a sequence that you don't have in the pool yet, because it's random. It's very efficient from the computational point of view, so you can generate a very large number of sequences in a very short time. And also, it's something that's very easy to implement. So that's why we chose this one. And the only difference we have compared to like the plain random insertion is that we leverage a little bit the structural info that we observe in the data. So for example, we know that the drivers or the sequences that we observe in the data start at a particular zone. So we encode this information within the heuristic to make sure that we fix those entry and exit stops when we generate sequence. But it's also drawn randomly from the data, from the set of stops that we observe in the data. Okay, so that's a pretty simple sequence pooler. And for the score model, we have a set of requirements. And the input of this model is going to be a pair of sequence and route, or a pair of solution and instance. And the output is a numerical score, which is going to describe how good this sequence is for that particular route. This can be measured, for example, as this expected deviation to this unknown optimal sequence that we have in the challenge. So accuracy is important for the score model, but more important, because in the context that this model is going to be used, is to select the best sequence. So more important is that you preserve the order, not much the accuracy. So if you have one one sequence better than the other, so you should reflect that in the relative scores outputted by the model. It needs to take into account the instance characteristics, and and it needs to be able to evaluate sequences in a relative fashion. Which means that if you have, for example, some feature in this model, like the duration of the route, the duration by itself doesn't say much whether it's a short route or not. You have to compare this duration with the duration of the other routes in the pool. So you have to somehow draw some statistics from the pool in order to be able to compare routes among them. For training a score model, we cannot train this directly on the given data, because there are no numerical scores there. So what we do is we propose a framework to expand the original data into something that we can train on. And that's the most important part of our submission, is this algorithm for, like we call it, the learning framework, in which we start with the original training set, with the set of routes made available. And we are going to expand this data into something that is a direct supervised learning problem with numerical dependent variables. So we are going to split the data into a number of batches. And we are going to process each batch iteratively. So first we are going to collect some structural info about this batch. So this structural info pertains to things like common entry and exit stops observed in the data, and also transitions, like from one zone to the other. So it kind of just a single pass through the data to count the number of transitions and count the number of entry and exit stops. And then for each route in each batch, we are going to use our sequence pooler to pull a number of sequences. We are going to compute some statistics on those sequences. And then for each sequence that we pulled, we are going to compute the score of this sequence. So we are going to, with this score metric, we are going to compare with the optimal sequence for that particular route. We're going to obtain a numerical score. We're going to get features from a vector of features that depend on the sequence itself, depends on the instance or the route, and depend on the statistics. So you can evaluate things in a relative sense. And we are going to add this data point to this regression model that once we finish all the batches and all the routes, we are going to train. And we are going to return, together with structural info about the whole thing. So that's the score model. And I guess the real question is whether this is going to lead us to something interesting after we train this model. And well, if we want to, if we want it to lead to something interesting, at least we should try to provide as much information as possible. So in this phase here, we just threw everything that we could possibly imagine that would affect how good the sequence is. So there are like a very large number of features at the level of the individual solution, from the pool statistics and from the instance itself. So in total, we have, like, considering combinations of these terms, more than 1,000 features in this model. And finally, the last part is the sequence selection. So basically, once we have this model trained, the only thing we need to do is, once we are given a new route, we are going to pull a set of sequences for this route, and we are going to evaluate each sequence under this score model and pick the best one. Right? We're going to trust the evaluation by the model and pick the best one. So I have, like, lines 3 and 4 here. You have something that just creates like a subset of the pooled sequences. And the reason why we have that is because in the challenge we have a very tight runtime constraint for returning a sequence for a route. And we wanted to make sure that we are not exceeding that. So we just constrains or just decreases the size of the pool, and then just selects the best sequence from what remains in the pool after this pruning step. Okay, so how well this framework perform? We tested it on the data of the challenge, and the first thing we did was to drop the medium and low quality routes because we were more concerned about training the score model and evaluating against the high quality routes. And we create some data sets from the original data. So we call them data sets A to E. So we used a stratified sampling strategy to guarantee that all zones were well represented, both in the training set and in the test set. Nothing special here. And then the score model is just a plain regression model. So we had some options to choose from. We evaluated different model architectures and model types, and we ended up using just linear regression with L1 norm regularization, which is the lasso regression. Gave best results overall, and also has a nice advantage in which it's very fast to evaluate the score of a sequence with this lasso model, because after you train this model, you have sparsity in the coefficients, which means that you can evaluate that much faster than if you use, for example, a neural network. All right, and so you have results on the test data, on these test data sets. We compare with some baseline. So baseline 1 is the near optimal TSP sequence. Baseline 2 is just a randomly selected sequence from our pooling method, which considers those entry and exit zones. And then there in the pool and select set of columns, the average 00474 is the score of the method once you use the score model. So all the gain from baseline 2 to the pool and select 00474 is attributed to the score model. And we spend more time, and that was after the submission, we spent more time trying to understand exactly how this model was performing and why it was like improving the performance of the whole method. We saw that there was some correlation, which in this case here is as we would like to see, right? So correlation between the actual scores and the predicted scores. But there was also a lot of noise. So I think the real question was how useful the model really is to identify the best sequence from the pool. And then we did some additional experiments, out of sample experiments, in which we created, for every route, we created a pool. And then we evaluated, and we also inserted the optimal sequence within the pool. And then we computed the number of sequences in the pool that were evaluated as better than the optimal sequence. So if the score model was perfect, then this ratio will be 0, right? There will be no other sequence in the pool better than the optimal sequence. And since we have noise in the model, we obtained, we couldn't obtain 0, but we had, in most of the time, we have the score model identifying this optimal sequence from the pool. And when this doesn't happen, then at least this optimal sequence is within like the top 5% of 10% of the sequences from the pool. So the model is really learning what are the quality of those good sequences. Yeah, so this is about the importance of the route duration. And for each data set, you see that duration ratio is basically the duration of the route compared to the very or a near optimal TSP solution for visiting the set of stops. And you see that there is clearly like very, very short routes are, at least on average, they are not the best thing to do. So usually you want to trade off route to duration by something else, but we don't know exactly what this something else is. The good thing about the lasso model is that also gives us the opportunity to interpret the importance of the different features that we fed to the model. And I find it quite interesting because this is a feature importance table. So we have the most important features for the prediction. And we have all the usual suspects here, right? So we have route duration appears as the most important feature, which is not really surprising. But then you start seeing things that make a lot of sense. For example, you have all those blue features, they correspond to zone transitions. So it basically means that if you have a lot of zone transitions, then you're gonna, like, this is not something desirable in a good sequence. You also have time window compliance, so you have a lot of time window violations, or if the magnitude of this time window violations is high, then this also is not good for the sequence. And you also have route inconsistency features for example, similarity to the training data. So you want to have sequences that are somehow similar to the sequences that you had before. So this also like justifies, because there is a lot of work on route consistency for VRP, and this sort of gives one very nice empirical justification for this work and highlighting that route inconsistency is really important. And the thing is that those things depend on the instance characteristics. So you have a lot of combinations here of features that are at the sequence level with features that are at the instance level, which shows that you cannot evaluate the sequence features isolatedly, but you have to take them into account together with the instance features to understand whether they are important, whether they are going to make your sequence better or not. Okay, so in the beginning, when I was talking about the pooling algorithm, I mentioned that we were discarding time windows because there was a very small ratio of time windows in the data. And here I basically show that we pay the price for that, that our algorithm is much better when we have instances with low number of time windows. And finally, yeah, that was our final position in the leaderboard. So we are there in the middle of the pack of the chasers. And it was, yeah, I mean, was like a pretty big gap to the winning teams. But we like to think that our method is general. So we try to use, or at least in, of course, that while we were developing this model, we were not thinking like that. It was only after that we thought, okay, we are doing something here that can be generalized. And then it's something that if you have a problem like that, this sort of GOP, generalized problem, you can solve this method as long as you implement those three simple ingredients, which is basically something to compute the dissimilarity between solutions, returning a numerical score measuring this dissimilarity. Domain knowledge to gather what could be potentially relevant features that impact the quality of your solution. So this is not directly encoding this knowledge in the algorithm, is just generating this set of features, these dimensions, so the model can learn what is important. So we're not telling what is important directly in the algorithm, is just giving the opportunity for the score model to understand what is important. And a solution generator, which can be any randomized heuristics, and like many meta heuristics and heuristics, they have a randomization component that could be readily used to create a large pool of randomized sequences or randomized solutions from which you can evaluate each of them and pick the best one from the score model. So yes, that's what I had to say about our submission. Thank you again for listening, and then happy to take any questions.
Thank you so much, Alexander. We have time for one question. So, just out of curiosity, so now you theorize the generalization. Have you tried in some other problem, or are you trying in some other problem?
We sketched how to do that for vehicle routing, but we haven't tried, like we haven't implemented. But we sketched that the ideas could be used for vehicle routing. If, for example, if you have a vehicle routing with multiple objectives that depend on the instance. So for example, if you have like sparse countersign instance, it's more important the route duration. If you have like very dense instance, then it's more important time window compliance. And then try this thing here by implementing those components for measuring the importance of those different characteristics depending on the instance. So we have like sketched how to do that, but we haven't had time to do that yet.
Is that a good item?
Yeah, good question. Yeah, it's if anyone is interested, they could share. Like.
Okay, maybe we have time for one quick question. Something in the audience. Alexander, thank you very much.
Take it. Yeah.